finally, in this lecture, I want to talk about one more important concept in statistical mechanics. This is the idea of the thermodynamic limit. So this is the last new kind of concept we will introduce today. And again, it's very important. The thermodynamic limit basically tells you that as the number of particles gets very large, in some ways, the behavior of the system gets simple. So I'm going to do an example of this, and in particular, I'm going to do a very simple example, which is called the ideal, and then in brackets, spin a half. Don't worry about this if you don't know what it means, but anyway, the ideal paramagnet. So this is a very simple system, which I actually talked about in the first presentation. I made a paper model of it here. So this is a one-dimensional paramagnet. I've got a system which is made up of spins, like this. And what spin half means is that each spin can either point up or it can point down. So that's it, right? It's up or down. So there's only two choices. It can either point up or down. So in this way I can get different microstates. This is an example of a microstate. This is another one. This is another one. So on. So I can scatter between different microstates in the system like this. So let's explain what this model means. There are n spins. That defines the microstate. Each spin only has two possible states. It's either pointing up or pointing down. But that's it. Those are the only two possibilities for this system. And the microstate is specifying the spin of the direction of every spin. So I say first one's up, second one's down, next one's up, next one's up, next one's down, next one's down. Specify. I tell you what every spin is doing. And the microstate changes by spin flips, same as in the presentation. So a certain spin can change from an up to a down. Microstate changes by spin flips. And this simply means that what was an up spin can become a down spin. Okay, so I said the goal of statistical mechanics is to be able to describe the behavior of the state, that's the macroscopic, the large-scale properties of the system, in terms of the statistics of the microstate. So it gives you a connection between what the microstate of the system is and what the macroscopic state of the system is. And I'll do now a very simple example of this for this paramagnet. So I'll define what I mean by the state of the paramagnet. The microstate tells you exactly what every particle is doing. The state is just something which is visible on the large scale. Now if you think about what this might be, each spin in this magnet generates a magnetic field, a very small magnetic moment. Okay, so this will generate a small magnetic field around it. Now, if they're all pointing in random directions, if half of them are up and half of them are down, then the net field is 0. So we don't measure anything. However, if by chance all of the spins, or the majority of the spins, are pointing up, say, you can have a few pointing down. But if the majority of the spins are pointing up, then this will generate a net magnetic field. And this we can measure on a large scale. So the thing that we can measure on a large scale is the net magnetization. This is like the average number of spins pointing up. I can't tell if an individual atom has spin up or spin down, but on a large scale I can see if most atoms are pointing up or if most atoms are pointing down. So this is the state of the system, and this is what's known as the magnetization, which I will give symbol little m, of course. Okay, and the definition I will give is a dimensionless definition of magnetization, which is slightly different from definitions you may find in solid state textbooks, for example. Anyway, the average that I will define it. Okay. So for each spin, let's say little number I, which goes from 1 to n, we define a number, Si equals, it's either plus 1 or minus 1. And it's plus 1 if the spin points up, and it's minus 1 if the spin points down. So this is just another way of label spins. Instead of talking about up and down, I can talk about plus 1 and minus 1. Then the magnetization is the average value of these S's. So it's defined as 1 over n, the total number of spins, times the sum, I equals 1 to n. That's the definition, and it's easy to see that for each spin which is up I get plus 1, for each spin which is down I get minus 1. Therefore this is equal to the number of up spins minus the number of down spins divided by the total number of spins. This first one's a definition. So this is the net number of arrows pointing, and this is something you can measure. Like I said, if most of the arrows are pointing up, this means that m is plus something. That means it will generate a magnetic field, and this I can measure. So this is a state property. It's a large-scale property of the system. Okay, so just to note, the value of m is always between minus 1 and 1. Right? Just from this formula here. N up plus n minus up down is n, so therefore this must be less than 1. And in particular, if m equals minus 1, then this means that every spin in the system is down. Right? So it must be minus, 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 minus. So if m is minus 1, then it means that every spin in the system is down. And if m is plus 1, it means that every spin in the system is up. And then in between you have a mixture of up and down. So if m is 0, then half of them are up and half of them are down. Okay, probably that's quite an important case. If m is equal to 0, then half of them are up and half of the spins are down. Right, so I've defined a very simple system then, the microstate is telling you what is every spin. The state is just telling you this magnetization, the average values of the spin. And I want to work out what's the connection between the two. Now, what does the fundamental postulate tell me? Okay. It says all microstates have equal probability. In this case, the spin flip means they're all accessible. And if I look at a particular spin, so let's suppose I choose to look at the first spin, why not? Then half of the microstates it will point down, and in half of the microstates it will point up. Because it's completely random, so in half of the microstates it must point down, and in half of the microstates it must point up. And they all have equal probability, so therefore the probability that the first spin is down is a half, and the probability that the first spin is up is a half. So it has equal probability to point up or down. So therefore the probability that Si equals 1 plus 1 is a half. The probability that Si equals minus 1 is a half. And this is true for each spin, so for all I equals 1 n. In other words, these Si are independent and these Si are independent and identically distributed random variables. Okay, and we can actually say what's the mean and what's the variance. Well, the average is obviously 0, because plus 1 or minus 1 are equal probability, so the average value is 0. And the variance is 1, right? Because it's Si squared times a half, plus Si squared times a half is 1. Now this is important because this is the condition for the central limit theorem. If I have a large number of random variables which are independent and identically distributed, then if I add them all together, which is what I do when I calculate the magnetization, the result must become normally distributed and it must have a certain mean and variance. So this is important because it allows us to apply the central limit theorem. Therefore, the central limit theorem implies that M, which is 1 over n plus 1 plus 2 n, where n is large, is approximately normally distributed, approximately normal. With the average value is just n times the average value of Si. Let me write it. It's 1 over n times the average value of S1 plus the average value of S2 plus the average value of n. Okay, but these are all 0, so this turns out to be 0. So, that's obvious, right? Lots of things have mean 0, you add them together, the mean must be 0. The variance is more interesting. So the variance of m, this is the variance of 1 over n s1 plus 2 plus n. If I multiply by a number in here, then the variance of this number is squared. So this is 1 over n squared times the variance s1 plus 2 plus n. Okay, so I don't think I actually stated this result, but it's not hard to prove. Straight from the definition, if I consider the variance of some number times a variable x, then this is equal to that number squared times the variance of x. Easily check that's true. Okay. But now these things are independent, so therefore we can just add the variances together. This is 1 over n squared times the variance of s1 plus the variance of s2 plus the variance of sn. And each of these is just equal to 1, and there are n of them, so this turns out to just be, write it down there, turns out to just be 1. Therefore the variance is approximately normally distributed, the mean is 0, and the variance is 1 over n. And remember that the variance is the width of the distribution squared. So this implies that it has a distribution width of order 1 over the square root of n. Okay, so I want to compare two situations. Firstly, if n is a small number, so there's only a small number of spins here, then m can only have a small set of values, and each of these values has a significant probability. On the other hand, if n is a very large number, so there are lots of spins, then I can use the central limit theorem, and then n is normally distributed and has decreasing width. So as I increase the number of spins, I decrease the width of the distribution. So let's compare the two cases when n is small and when n is large. Right, so I'll do a graph. What's the probability of having magnetization m as a function of m? And I already told you m is between +1 and -1. If the number of spins is small, then there's only a small number of values that m can take, and they all have a significant probability. So you get a graph of something like this. In fact, the shape is exactly the same as the shape of a binomial distribution, for reasons which are hopefully clear. In particular, if m is small, you have a large range of possible values of m. Okay? So m can be 0, but it can also be quite likely to be here or here. There's a large range of possible, a large range of likely, let's say, values of m. And now let's compare this to the case of large number of spins In this case, we say it's approximately a normal distribution, and the width is approximately the square root of n. So you get a distribution which is like this. And I told you that the width here is the order of 1 over the square root of n. Now the point is that, the important point is that this width is incredibly small. If I have a normal size magnet, like the sort of magnet I might just hold in my hand, then n will be about 10 to the 26. There's a huge number of atoms in a small amount of material. So if I have a small magnet, n will be about 10 to the 26, which means that this will be about 10 to the minus 13 for a handheld magnet. Simply because the number of particles in it are so large, right? So, for a system of only reasonable macroscopic size, this width is incredibly, incredibly thin. That means that the probability of 0 is almost equal to 1. So the only likely value of m is 0. So for large n, the only likely value of m is m approximately equal to 0. So this means that, in some sense, the system with a large number of particles is actually simpler than the system with a small number of particles. In the system with a small number of particles, m can be many different things. We can measure m equals plus 1 with a reasonable probability, m equals minus 1 with a reasonable probability, and a range of values in between. But in the large system, it's much simpler. In the large system, we only get m equals 0. That's it. So therefore, the large system is actually simpler, and in particular, in the small system, we have to consider m as a random variable, which can take a range of possible values. But in the large-scale system, we can consider m as just a number. It's just 0. So this is the simplification, and this is the part of the thermodynamic limit. So here, we need to consider m as a random variable, which can take a range of possible values, all of which have significant probability. But in this case, we can consider m just as a number to a good approximation. M as a definite number. So we lose the probabilistic aspect in the large scale. M is approximately 0 to a very good approximation. And this we see repeated in all of the systems we look at in statistical mechanics. You start with a state property, for example, the magnetization here, or something like pressure in a gas. If the number of particles is small, then there are a wide range of possible values of the variable. But if the number of particles is large, then it has almost exactly a well-defined value. So therefore, in a large-scale system, these state properties take on definite values, rather than having a probability distribution. This is called the thermodynamic limit. An example. So I can explain it briefly like this. What do we mean by the thermodynamic limit? As the system size goes to infinity, the number of particles gets very large. A state property goes from a random variable where we have to consider to approximately, so a random variable where we have to consider a range of possible values, to approximately a definite value. So this is the heart of it. As the system size gets large, we can replace probability with definite values in our theory. And we'll do this for a gas and so on later on. Okay, in fact, let me very briefly explain that. Pressure in a gas. So what is pressure? Why do we feel pressure in a gas? We feel pressure in a gas because inside the box I have particles, okay? And these particles hit the edge of the box, right? They fly around at random, but sometimes they hit the walls of the box. When the particles hit the walls of the box, they are bounced back by the atomic forces, and therefore the particles exert a force on the box. So the pressure is simply the force of atoms, particles in the gas, bouncing off the walls of the box. If n is small, then that means that in any amount of time, the number of collisions is small. So you get a bump when a particle hits the box, then you get nothing. Then you get another bump, then another particle hits the box, and then you get nothing, and so on, right? So if you were to draw a graph of the pressure, this is the force on the walls of the box, as a function of time, it would look something like this. You get times where a particle hits the wall of the box, and you suddenly get a big pressure. Then there'd be nothing, and then another particle will hit the wall of the box, and then another particle will hit the wall of the box, and something like this. So each time a particle hits the wall of the box, you get some force, which is related to the velocity of that particle, and it's very complicated. Because sometimes many particles hit the wall, sometimes they don't, and so on. However, if the number of particles in the box is very, 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 very large, okay, then at any point in time, I have a large number of particles colliding with the wall of the box. The number of the particles is large, and these particles are all flying around in different directions, right? At any point in time, I have many particles colliding with the wall in the box. Therefore, the force of each of these particles averages out. So in this case, if I draw the pressure as a function of time, I get roughly a constant value with some variation. Such a large number of particles are hitting the walls of the box that the effects of all of these particles average out, and as a result I get a constant number. Okay, hopefully that makes sense, right? If there are a few particles, sometimes a particle hits the wall, sometimes it doesn't, and you get this complicated behavior. If you have a large number of particles, then all of the time particles are hitting the wall of the box, so you get a roughly constant pressure. Now this is another example of a thermodynamic limit. For small n, it's a complicated random function. But for large n, it's approximately constant. And this is exactly the same behavior we saw in the paramagnet. For small m, it has a range of possible values, but for large m, it takes on a definite value. So this is the key to the thermodynamic limit. If the number of particles is large, then the state properties can be described as approximately definite numbers, when in fact they are really probabilities depending upon the microstate. Okay, so in the coming weeks, these are the key concepts, and we've introduced most of them in this lecture. So the first is the fundamental postulate. You look at the number of microstates, which is very large, and each microstate will have an equal probability. Secondly, this idea of the thermodynamic limit, if the number of microstates is large enough, then the state properties, the large-scale properties of the system, take on definite values because of some averaging. So those are the two key concepts. That's a good place to finish. So in the next class, I'm going to develop these ideas a bit more, particularly looking at the example of the paramagnet.